Hello everyone, let me start by expressing how honored we are to be part of this year's World Automation Congress and to present our research paper, Real-Time, Short and Open Circuit Fault Detection with Fault-Tolerant Topology in Single-Phase Inverters. My name is Shuaib and I am a PhD student at the University of Rouen, Normandy. The author of this paper are myself, my supervisor Dr. Kambi Sterani, Dr. Khalil Idrisi from the Clermont-Auvergne University, and Mr. Nouman Khan from Pakistan Institute of Engineering and Applied Science. In this presentation, we will start by explaining the objective and motivation behind this work. After that, we will describe the method for open circuit and short circuit fault detection, as well as the fault tolerance topology. Then we will discuss the results of the conducted simulations, and finally we will conclude with our findings. Power converters are essential components in many electrical systems. For instance, in an aircraft powertrain powered by a fuel cell, various types of converters are integrated throughout this powertrain. AC-DC converters, DC-DC converters, and so on. The reliability of these power conversion systems heavily depends on the reliability of the power converter themselves. So given the critical importance of these systems in applications such as aviation, it is crucial to prevent all types of failures and ensure normal operations. Research indicates that approximately 21% of converters failures are due to damaged semiconductor devices, with semiconductor faults primarily manifesting as short circuit faults and open circuit faults. These failures are particularly critical and challenging to handle, as abnormal overcurrent may lead to severe damage to system components. Now for the motivation and methodology. To increase the reliability of power converters in power conversion systems and to ensure the continuous delivery of the correct voltage to critical loads, fault detection for open circuit and short circuit failures must be fast, and fault tolerance topology must be applied immediately. In this work, we focused on H-bridge single-phase inverters, which are widely used in various electrical systems such as renewable energy systems, electrical vehicles, industrial motor drives. Our goal was to propose a fault-tolerant topology that enables the inverter to continue operating even after a fault has occurred. To achieve this, open circuit and short circuit failures must be detected in real time, focusing on short circuit failures, which can cause immediate and severe damage if not addressed properly. So as mentioned before, the fault detection needs to be fast and in real time. That's why we used a straightforward approach online or voltage measurement across the switches and the knowledge of the gate pulse signals. For example, a short circuit failure is detected in a switch if the voltage measured across this switch and the voltage measured across this switch in the same leg are smaller than a threshold, while the gate pulse signal is low, meaning the switch is supposed to be open. If these two conditions are verified for a period of time, a short circuit failure is confirmed. On the other hand, for an open circuit failure is detected if the voltage measured across the switch is greater than a threshold, while the gate pulse is high, meaning the switch is supposed to be closed. This threshold is estimated to be 0.8 of the input voltage. After the fault has been detected, either a short circuit or open circuit failure, a fault-tolerant strategy is then applied. This is achieved by adding a redundant floating leg that can replace the faulty leg. So in the fault-free condition, the two primary legs remain connected via SW1 and SW3, while the floating leg is disconnected. Additionally, the command signals in the two transistors of the floating leg are set to 0. Now, in the event of a fault, short circuit or open circuit in the right leg, this SW1 is open to isolate the faulty leg, SW2 is closed to connect the floating leg, and SW4 is connected to the filter inductor. The upper transistor of the floating leg is controlled by PWM1, which is used to control T1 in the fault-free condition, and the lower transistor is controlled by PWM2, which is used to control T2 in the fault-free condition. Now, in the event of a fault in the left leg, SW3 is opened and SW2 is closed to replace the faulty leg, and SW4 is connected to the filter capacitor. The top transistor is controlled by PWM3, which is used to control T3, and the bottom transistor is controlled by PWM4, which is used to control T4 in the fault-free condition. The fault-tolerant strategy is summarized and visualized here in a state flow chart created using MATLAB Simulink. The inputs to the system include the gate pulse signals, PWM, used to control the primary switches of the inverter, the voltage measurement across the switches T1, T2, T3, and T4, and the outputs are the indicators for short circuit failure and open circuit failures, where 0 represents no fault and 1 indicates the presence of a fault. We have also the control commands for SW1 and SW3, which are isolation switches to determine which leg to disconnect in the event of a failure, and also SW2 and SW4, which connect the floating leg in case of a failure. We have also gate pulse signals for the transistor in the redundant leg as outputs. To test the effectiveness of the fault detection method and the fault tolerance topology, a Simulink model of single-phase inverter along with the redundant leg was developed. The parameters used in the simulation are shown in this table, and the logic behind the fault detection and the fault tolerance topology was modeled using a flowchart as explained earlier. Now for the gate pulse signals, a double sinusoidal modulation was used. It consists of comparing a sine wave, the signal to be synthesized, with a carrier. In our case, it was a triangular signal. The output signal changes state from 0 to 1 and from 1 to 0 each time the modulator and carrier intersects. We also introduced a delay dead time to prevent short circuits in the inverter. Now, to assess the effectiveness of this method, a Simulink model was developed and tested under several scenarios. In the first scenario, the model was tested without any faults to establish a baseline for comparison. In the second scenario, a short circuit failure was introduced in T1 by forcing its gate pulse signal to 1 after 0.01 seconds. And in the third scenario, an open circuit fault was introduced in T3 by forcing its control signal to 0 after 0.01 seconds. And finally, in the last scenario, an open circuit fault was introduced, but this time the redundant leg was used as a fault-tolerant strategy. Here we have the results for each scenario displaying the output voltage, the gate pulse signals, and the indicators for short circuit and open circuit failures. In the first scenario, when no fault was introduced, we observed that no fault was detected and the output voltage remained clean sine wave as expected. In the second scenario, a short circuit failure was introduced and we can see that the fault was correctly detected and located. We can also see that the output voltage shows an asymmetrical sine wave, which is a direct consequence of a short circuit failure. And now for the third scenario, where an open circuit failure was introduced in T3, we can see that the fault has been detected immediately, but the redundant lag wasn't used, and that's why the negative half cycle is missing in the output voltage. In the last scenario, the redundant lag was used, and the method successfully detected the failure immediately and adjusted the inverter topology to guarantee an output voltage similar to that of a normal operating mode. Now we finish with the conclusion and some perspectives. In this work, a fault-tolerant topology for an H-bridge single-phase inverter was proposed. This topology includes a floating redundant lag that can replace the faulty lag in case of any failure, short or open circuit. For the fault detection, a simple approach based on the voltage measurement across the switches was used. The key advantages of this method is that it allows for immediate and real-time fault detection, which enables the redundant lag to intervene quickly. Also, this approach ensures the continuity of the correct voltage delivery to the load, preventing interruptions. For the future work, we can focus on reducing the number of sensors used in the fault detection to reduce the costs, and we can also work on extending this fault tolerance strategy to more complex inverter topologies, such as an H-bridge multi-level inverter. Thank you for your attention, and feel free to ask any questions.